All right, getting back to chapter 15, 16, 16? 16, yes, 16.3. Shared state concurrency. Close that. Message passing is a fine way of handling concurrency, but it's not the only one. Consider this part of the slogan from the Go language documentation again. Do not communicate by sharing memory. What would communicating by sharing memory look like? In addition, why would message passing enthusiasts not use it and do the opposite instead? In a way, channels in any programming language are similar to single ownership because once you transfer a value down a channel, you should no longer use that value. Shared memory concurrency is like multiple ownership. Multiple threads can access the same memory location at the same time. As you saw in chapter 15, where smart pointers made multiple ownership possible, multiple ownership can add complexity because these different owners need managing. Rust type system and ownership rules greatly assist in getting this management correct. For an example, let's look at mutexes, one of the more common concurrency primitives for shared memory. And that was the big intro. We're pretty much just looking at mutexes, locks, and whatnot. But yeah. Using mutexes to allow access to data from one thread at a time. Mutex is an abbreviation for mutual exclusion, as in a mutex allows only one thread to access some data at any given time. To access the data in a mutex, a thread must first signal that it wants access by asking to acquire the mutex's lock. The lock is a data structure that is part of the mutex that keeps track of who currently has exclusive access to the data. Therefore, the mutex is described as guarding the data it holds via the locking system. So yeah, basically just like they described here, they're just going over what a mutex is. And a mutex is a locking mechanism. So let's say you have multiple threads trying to access this one piece of memory. Well, you don't want all of them to access this one piece of memory at once. You want one of them to access it at once because you don't want data races and all other stuff. So one way of solving that problem is to lock that piece of structure that's going to be accessed so that only one thread can access it at a time. And that essentially is what a mutex is. Just a lock and unlock mechanism. Mutexes have a reputation for being difficult to use because you have to remember two rules. One, you must attempt to acquire the lock before using the data. Two, when you're done with the data that the mutex guards, you must unlock the data so other threads can acquire the lock. Alright, so there's two rules. The first one, which they pretty much stated, is you have to ask for permission to use the lock because somebody else may be using it. And if somebody else is using it, then you can't use it. Rule number two, once you have the lock and you do what you need to do, let other people know that you're done with it so they could use it and access that piece of memory. For a real-world metaphor for a mutex, imagine a panel discussion at a conference with only one microphone. Before a panelist can speak, they have to ask or signal that they want to use the microphone. When they get the microphone, they can talk for as long as they want to and then hand the microphone to the next panelist who requests to speak. If a panelist forgets to hand the microphone off when they're finished with it, no one else is able to speak. If management of the shared microphone goes wrong, the panel won't work as planned. That's a really good metaphor. Yeah. So they described it as having a panel of people and only one microphone. And it's assumed that you can only speak when you have the microphone. So one person's speaking, they have the lock. And then when they're done, they could pass it off to somebody else so they have the opportunity to speak. But only one person speaking at a time. Good job. Management of mutexes can be incredibly tricky to get right, which is why so many people are enthusiastic about channels. However, thanks to Rust type system and ownership rules, you can't get locking and unlocking wrong. That's a strong claim. Ooh, let's see what happens. The API of mutex. As an example of how to use a mutex, let's start by using a mutex in a single threaded context as shown in listing 16-12. And we have some source code, so let's write it out. So what they have here, we're going to import sync mutex. Got it. And then in our main, mutex new 5. Not sure what the 5 is for. Let me mutable mutex lock unwrap. Oh, I see. So what they did here is they have a mutex, they have the new, and then they have the data that the mutex is guarding. And then right here, they acquire the lock, and then they modify the inner value from 5 to 6. And then once the scope is done, they know that the lock is no longer required and other people can use it, seemingly. That's what I'm getting from this. But let's write that out real quick. Actually, let's just copy it. It's pretty straightforward. And let's run it. Cargo run. And then we have it, mutex data 6. So yeah, this 5 is the data that was passed in that's being cared for by this guardian. Okay. As with many types, we create a mutex using the associated function new. To access the data inside the mutex, we use the lock method to acquire the lock. This call will block the current thread so it can't do any work until it's our turn to have the lock. And this is probably where all the magic happens. Oop, I didn't mean to do that. So basically what they're stating here is that this call to lock, this is how you make sure that you can acquire the lock. This is you asking for it. But this call is going to block until the lock is freed and you can use it. So if somebody else is currently has already acquired it, in this thread, when we're gonna wait until that thread is done with it, so then we can use it. That's ingenious. I like that. The call to lock would fail if another thread holding the lock panicked. In that case, no one would ever be able to get the lock. So we've chosen to unwrap and have this thread panic if we're in that situation. That is interesting. So they're explaining the need for the unwrap, right? So the scenario as they're painting it is there are multiple threads trying to access this lock. One of them that previously had this lock panicked. So what happens then when the next person tries to acquire the lock? Well, nothing's going to happen. It's going to give an error. So we unwrap it if that situation happens. Seemingly. But what I'm confused about is if the previous thread panicked, why does the previous thread still throw the panic and all that garbage out to the screen and fail? Or does this mean all threads panic that try to acquire the lock? I'm not sure. After we've acquired the lock, we can treat the return value named num, in this case, as a mutable reference to the data inside. The type system ensures that we acquire a lock before using the value in m, mutex, is not an I32. So we must acquire the lock to be able to use the I32 value. We can't forget, the type system won't let us access the inner I32 value otherwise. Alright, so basically what they're saying here is kind of what we already said, but they're going over how their API for mutex, this unlock and unwrap, and then this thing in the scope, enforces the rules, the 2 rules for mutexes, which the first one was you have to ask for permission to acquire the lock. And then the second one was when you're done with it, you give the lock, you pass the lock to the pool and let whatever thread who wants to use it next, use it next. The way Rust, I guess, ownership works, they've ensured that you can never forget to do either of those 2 things. And then they also mentioned that once you acquire the lock, then you could access the inner value, the data, as a mutable reference, which they did here. That's why they changed the 5 to 6. Show you as an example. Continuing on. As you might suspect, mutex is a smart pointer. More accurately, the call to lock returned a smart pointer called mutex guard, wrapped in a locked result that we handled with the call to unwrap. The mutex guard smart pointer implements deref to point at our inner data. The smart pointer also has a drop implementation that releases the lock automatically when a mutex guard goes out of scope, which happens at the end of the inner scope in listing 16-12. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by other threads because the lock release happens automatically. And then after dropping the lock, we can print the mutex value and see that we were able to change the inner value, the I32, to 6. They're just rehashing what we already said, but they gave us some more context. So here we can actually see it. They said that the mutex is a smart pointer, which we could have guessed, and the lock returns a smart pointer called mutex guard. And here in the editor, we can see that it did return a mutex guard. However, we named it num and we were able to access it, the inner data from it, which means that the mutex guard implemented deref, which allows us to point from mutex guard to the inner value, which is the I32 value, and change that. And like we already guessed, they implement drop so that the lock releases when the variable, or this thing, m, the lock, the scope, when it ends. And then the lock gets released so that everybody else can use it. So they've explained that here. We've stated it, but they're explaining it here. One thing I don't know about is the lock result, which we handled. Oh, I see. So yes, we do have a mutex guard, right? But that's after we've unwrapped the result. We had the locked result that we unwrapped, and if it would panic, it would panic. But we have something there, and they returned a mutex guard. I got it. All right. Sharing a mutex between multiple threads. Now let's try to share a value between multiple threads using mutex. We'll spin up 10 threads and have them each increment a counter value by 1. So the counter goes from 0 to 10. Note that the next few examples will have compile errors, and we'll use those errors to learn more about using mutex and how Rust helps us use it correctly. Listing 16-13 has our starting example. So let's make this big so we can just see the entire example. And as they noted, this is going to have errors. But let's read through this first. We have a mutex, we have our thread, you have the value starting at 0, which is the data, a vector of handles, we have no type assigned to it yet, and then for 0 and 10, so in this range, we're creating threads, and we're moving the context to it. Context is being counter is being moved to the threads. We lock it, we require the lock, we unwrap, and then we do a +1. And we're pushing, so this is the code for each of the threads that are being spawned, right? That's this, where they acquire the lock and they do a +1. And we're pushing that all to the handle, so we have our list of threads. And then for handle and handles, we join and unwrap, so we're running each of the threads, seemingly. I see. And then we have, at the very end, we want to see what the value is of this data. Let's write this out. Add a new import, use std thread, that counter mutex new. Oh, this is supposed to error out. Yeah, that's what I forgot. Let's see how it errors out. It could be erroring out because it's not being passed by reference. I don't know. 10. Let handle equal thread. Spawn, move, the mutable num equal counter that we want to require the lock. Then we want to unwrap it. Yeah, you can see the result right there. This is the lock result. Oh, hold on. Yeah, right here you can see the lock result. We have result mutex and then poison error. Wow. I don't know why they call it poison error, but that's kind of cool. Unwrap. And then we have a reference to num plus equal 1. Handle stop push. And now once we do the push of the handle, we now have a type for our vector. So just as you can see that prior to this, the vector didn't know what it was going to be. Handle, now it does. And then last but not least, that for loop ended, right? Ooh, it did not. I'm not even all the way to the left. That's why it looks weird. All right. Then for handle in handles, handle dot join unwrap, and then print the value. I could write this one, but yeah. Okay. Okay. So I believe we have everything here, and we're expecting it to error. So let's see what the error states. Invalid expression for the left side. Mutable counter that lock. Binary can't be applied. That might not. Is that the +1 push handles unlock might be missing. Okay, we knew it was supposed to error, but I'm not sure if that was the error that we're supposed to get. Let's read on and find out. We create a counter variable to hold an I32 inside a mutex, as we did in listing 16-12. Next, we create 10 threads by iterating over a range of numbers. We use thread spawn to give all of our threads the same closure, one that moves the counter into the thread, acquires a lock on the mutex by calling the lock method, and then adds 1 to the value in the mutex. When a thread finishes running its closure, num will go out of scope and release the lock so another thread can acquire it. So yeah, they're going over the code, and they said counter got moved into the thread. That sounds kind of awkward, but okay. In the main thread, we collect all the join handles. Then, as we did in listing 16-2, we call join on each handle to make sure all the threads finished. At that point, the main thread will acquire the lock and print the result of the program. We hinted this example wouldn't compile. Now let's find out why. So their error and my error look slightly different. We have counter value captured after move. Move occurs, doesn't have a copy trait, so you shouldn't be able to move it in there, which I stated earlier. And that is the only error they have. So I must have wrote something incorrectly. Quickly scan through. No, it looks like I wrote everything correctly, but just in case, I'll copy and paste the inner main method. See if I get the same error. Paste. And I must have wrote something wrong because this is the exact error they have, which is a different error than what I had. Okay, sure, I mistyped something. So now that we have the error, we can move on. The error message states that the counter value is moved into the closure and then captured when we call lock. That description sounds like what we wanted, but it's not allowed. Yeah, it shouldn't be allowed. Let's figure this out by simplifying the program. Instead of making 10 threads in a for loop, let's just make 2 threads without a loop and see what happens. Replace the first for loop in listing 16-13 with this code instead. Handle 1, handle 2. I see. Copy that. For loop. Gone. So we replaced the for loop, which was creating 10 threads, and now we just manually created 2 threads, and we're going to run them. Just simplifying the problem. And it looks like we have issues with ownership and borrowing. That makes sense. We make 2 threads and change the variables names used within the second thread to handle. Wait. They changed more than just that? I know we just copied and pasted this in, but let's review it real quick to see what exactly they changed, because I think they changed something else now. Handle, thread. This is the same closure. Push. Handle thread. In this closure, they changed the value from num to num2. Okay, I'm not sure if that makes a difference, but okay. We made 2 threads and changed the variable names used with the second thread to handle2 and num2. When we run the code this time, compiling gives us the following. Move value, captured after move, no copy trait. This is for num2. Handles thread, counter, no copy. And just to confirm, we have about that same thing here. The syntax is a little different, but it says the same thing. Cool. Aha! The first error message indicates that counter is moved into the closure for the thread associated with handle. That move is preventing us from capturing counter when we try to call lock on it and store the result in num2 in the second thread. So Rust is telling us that we can't move ownership of counter into multiple threads. The ownership rules. This was hard to see earlier because our threads were in a loop, and Rust can't point to different threads in different iterations of the loop. Let's fix the compile error with a multiple ownership method we discussed in chapter 15. Okay. Oh, that makes more sense. Multiple ownership with multiple threads. In chapter 15, we gave a value multiple owners by using the smart pointer RC to create a reference counted value. Let's do the same here and see what happens. We'll wrap the mutex in RC in listing 16-14 and clone the RC before moving ownership to the thread. Now that we've seen the errors, we'll also switch back to using the for loop, and we'll keep the move keyword with the closure. Okay, so more or less, they're saying one of the major errors here were that we moved the counter, the mutex, into each of the threads, which gave the thread ownership of the counter, and then another thread tried to act on the counter. No good. Can't do that. So they want us to use RCs and start doing reference counting, and then pass the reference into the thread and then see if that works. It sounds like it should work, but let's see what happens. Let's read through this real quick too. We have RC, we have our mutex, we have our thread. This is the same as before. We have our handles. They put the for loop back, but before the for loop we have a counter. We clone it, and then that counter gets passed into here. So now each thread has a clone of the counter. And we push the handles, then we call join, and we do the result. I'm just gonna copy and paste that because writing the same thing over and over again is kind of annoying. Control copy, paste. Ooh, terminal. Cargo run. And we get another error. I see. The error we have now is because RC is not thread safe, which is they mentioned in the chapter. So instead of using RC, we probably have to use something like, what is it called, ARC? A thread safe version of it, which they didn't introduce to us yet, but that's probably next. Once again, we compile and get different errors. The compiler is teaching us a lot. The trait bound RC is not satisfied in blah 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 blah. That doesn't, I don't know what that means. And then right here, RC mutex cannot be sent between threads safely. And because it can't be sent between threads safely, we can't do it this way either. But what do they say in the help? They are stating that the marker trait is not implemented for RC mutex, probably just not for RC. Required because it appears within the type. Okay, so it seems as though we're missing a trait to make this thread safe. Wow, that error message is very wordy. Here are some important parts to focus on. The first inline error states standard library RC standard library sync mutex cannot be sent between threads safely. The reason for this is in the next important part to focus on, the error message. The distilled error message states the trait bound send is not satisfied. We'll talk about send in the next section. Wait, where is send mentioned? Closure. I see a trait. Oh, I have to scroll over. There it is. The trait is send. Oh, okay, that makes sense. And is that here too? Right here, send. Cool. The trait send is not implemented. And they said we'll talk about it in the next section. Meh. It's one of the traits that ensures the types we use with threads are meant for use in concurrent situations. Unfortunately, RC is not safe to share across threads. When RC manages the ref count, it adds to the count for each call to clone and subtracts from the count when each clone is dropped. But it doesn't use any concurrency primitives to make sure that changes to the count cannot be interrupted by another thread. This could lead to wrong counts, subtle bugs that could in turn lead to memory leaks or a value being dropped before we're done with it. What we need is a type exactly like RC, but one that makes changes to the ref count in a thread safe way. And ARC. And the A stands for atomic. Makes sense. Okay. Fortunately, ARC is a type like RC that is safe to use in concurrent situations. The A stands for atomic, meaning it's an atomically referenced counted type. Atomics are an additional kind of concurrency primitive that we won't cover in detail here. See the standard library documentation for standard library sync atomic for more details. At this point, you just need to know that atomics work like primitive types, but are safe to share across threads. All right, so what they're saying here is that for reasons that they were previously stated, we can't use RC. RC is just not thread safe. But we need something exactly like RC that is thread safe. And they have that. It's called Arc. And it's in the standard sync atomic module library. And atomic, seemingly the things that are in there work exactly like the primitives that they mirror, but they are thread safe. So whenever you need thread safe items that you're going to pass around, you should probably look into there first to see if they exist. Also, they're not going to explain anything about thread safety, atomic packets library in this thing. They didn't even give us a chapter. They said see the standard library documentation. Okay. But moving on, we got the gist of it. We're going to use Arc instead of RC. Got it. You might then wonder why all primitive types aren't atomic and why standard library types aren't implemented to use Arc by default. I'm not wondering. It's probably overhead. Makes sense. The reason is that thread safety comes with a performance penalty that you only want to pay when you really need to. If you're just performing operations on values within a single thread, your code can run faster if it doesn't have to enforce the guarantees atomics provide. And just like I guessed, the reason why these are separate out into its own packets is because the overhead. They probably just slow it to run, which they confirmed. You don't want the overhead of enforcing these guarantees if you're only writing single-threaded code. Let's return to our example. Arc and RC have the same API, so we fix our program by changing the use line, the call to new, and the call to clone. The code in listing 16-15 will finally compile and run. And here we go. Oh, yeah, got rid of an entire line. And here we add Arc. Came right up. And then whatever there's RC, we now have an Arc. And it's great that they have the same API because now they're just interchangeable. We have RC here, place it with Arc. Do we have another RC? Do we? They said 3, 1, 2, and 3. I think that's it. Let's try to run it. Result 10. Bam, it worked. Ta-da! So the moral of the story is mutex has to be passed into the different threads that it's being used, and you can't pass it directly in because that breaks ownership rules. So you have to use reference counting. We learned about reference counting with RC. However, RC is not thread safe. But Arc is thread safe. Just a complete copy of RC with some extra guarantees. So if we use mutexes with Arc, everything's good. The code will print the following, and we saw that right here, result 10. I think that's the last bit of code, so I'm going to make this bigger. We did it! We counted from 0 to 10, which may not seem very impressive, but it did teach us a lot about mutex and thread safety. You can also use this program structure to do more complicated operations than just incrementing a counter. Using this strategy, you can divide a calculation into independent parts, split those parts across threads, and then use a mutex to have each thread update the final result with its part. Yeah, the structure of how we wrote our program makes sense. You can use that in many other ways while still using mutex that are much more complicated than incrementing a counter. I give you that. Similarities between refcell, RC, and mutex Arc. You might have noticed that counter is immutable, but we could get a mutable reference to the value inside it. This means mutex provides an interior mutability, as the cell family does. In the same way we use refcell in chapter 15 to allow us to mutate content inside the RC, we use mutex to mutate content inside an Arc. So right now they're just drawing the parallels, which one thing I did forget to mention this, but yeah, that is a thing. Mutex was immutable, so let's go back to our program real quick. When we define the mutex right here, right, it does not have a mutable keyword here, so it is immutable. However, we've been getting stuff from inside of it and then changing it, which means that it has interior mutability by definition. So that's what they were pointing out here. And they were drawing the parallels between RefCell and mutex because they're both doing interior mutability. And they haven't really mentioned it yet, but RC and ARC, which we know are pretty much the same thing, but one has thread safety. Another detail to note is that Rust can't protect you from all kinds of logic errors when you use mutex. Recall in chapter 15 that using RC came with the risk of creating reference cycles, where two RC values refer to each other, causing memory leaks. Similarly, mutexes come with the risk of creating deadlocks. These occur when an operation needs to lock two resources and two threads have each acquired one of the locks, using them to wait for each other forever. Ouch. Yeah, that line is hard. Ooh, deadlocks. So the way they define deadlocks, at least in this scenario, is that you have two locks, right? And you have two resources. And then the unlocking and locking of them sort of depend on each other in such a way that this one can't move forward and this one won't unlock because of that one. Like that interdependency. That's just a logic error. And that will just kill your program. If you're interested in deadlocks, try creating a Rust program that has a deadlock, then research deadlock mitigation strategies for mutexes in any language, and have a go at implementing them in Rust. The standard library API documentation for mutex and mutex guard offers useful information. We'll round out this chapter by talking about the send and sync traits and how we can use them with custom types. That is the end of this section, and the next section is going to be send and sync. So I'm looking forward to that because if I can write custom code that is thread safe, that sounds amazing to me. So I'm looking forward to that. But outside of that, this is the end of the video. I hope you liked it. I hope you enjoyed it. If you did, hit the like button, subscribe. Outside of that, peace.